My name is John Noguera. I am the Chief Technology Officer and co-founder of SigmaXL. We're going to be showing you some new case studies. Some of you may have attended previous webinars. There'll be a little bit of overlap because I do want to just show some of the introductory material, kind of a little bit of background on Monte Carlo simulation and optimization. So as I said, introduction to DiscoverSim, Monte Carlo simulation, a brief discussion on optimization, and we're going to look at three examples: profit simulation, magazine production optimization, and project selection. To start with, why do we need simulation? Why do we need Monte Carlo simulation? If you're, for example, in a Six Sigma project or doing design for Six Sigma, typically design of experiments is a very important part of the project, and that will result in an equation, a y equals f of x. And that equation is very useful for determining what to work on. However, one of the things that it doesn't readily answer is what happens if I cannot hold those x's completely or control those x's completely. That is, there's variation or uncertainty in the x. And this is where Monte Carlo simulation comes in, because it allows you to see what happens when you have uncertainty in your axis. So that's really the key here, that area, and allows you to deal with that uncertainty, quantify it, and manage it. Some of the features of DiscoverSim: we do use Six Sigma language, so instead of assumptions, we use the term inputs and outputs. We have 53 continuous distributions, 10 discrete distributions. You can specify correlations between inputs. It's fast. We have an Excel spreadsheet interpreter, so the calculations are actually done outside of Excel and then brought back in. Sensitivity analysis is included so that you can identify your important x's. Global optimization allows you to solve difficult problems and allows you to optimize statistics such as process capability. We have various techniques to do global optimization. These include dividing rectangles, a genetic algorithm, and sequential quadratic programming. I'm not going to get into the details of these, but essentially what you have are three very good optimization methods. The first one, direct, is very useful for covering a broad space. The genetic algorithm is the workhorse. It uses the evolutionary principles to solve difficult nonlinear problems. And then finally, fine-tuning can be done with sequential quadratic programming. As I mentioned to you, we use an outside engine called Gauss by Aptech. There's a very good random number generator built into that. It's also a very powerful computation engine, and that is where the actual core calculations are done. So that's all outside of Excel and then brought back in. You don't see that as a user. A wide variety of distributions. I'm not going to go through all of these, but basically you have the commonly used ones: normal, triangular, uniform. This one's nice, Pearson family. You can plug in a mean, a standard deviation, skewness, and kurtosis, and those four moments will then can be simulated. All right. Custom continuous is another one that you can use. Then there's a whole bunch of advanced continuous. I won't go through the list. And then we have discrete, and one of the distributions we'll be looking at today is this custom discrete. Okay, so that's our list of distributions. And why Monte Carlo? Well, as I mentioned, if you have a y equals f of x, of course, we assume that y equals f of x model is correct. So whether it's a design of experiments or a regression analysis or theory, one of the assumptions is that you have validated that model. So you have a good working model. It doesn't have to be a perfect model, but it has to be a good functional model. And now the next step is, how do we deal with the uncertainty in the x's? Okay, so that's where we're going here. So I cannot hold x constant. I have some uncertainty in the x. How do I then quantify my risk? And that's where Monte Carlo simulation comes in to help us. So a little bit of background on how how Monte Carlo simulation was named. It was in homage to the Monte Carlo casino. And here's an illustration of how it works. So I have three inputs: a normal distribution, a triangular distribution, and a uniform distribution. And what we do is this is what's called the transfer function, or the y equals f of x. and it's simply the sum of the three numbers. Okay, so it's a really simple transfer function, but the problem is, you know, mathematically you could, this is actually still a fairly simple problem and one could solve it mathematically, but what's nice is that essentially by brute force, by taking a random sample from the normal distribution and a random sample from the triangular distribution and a random sample from the uniform distribution, you sum those three and then you have a single Y output. And then you repeat the process 10,000 times. And then after you have that, this is your output, your Y, you can then look and you can see the mean, the standard deviation, normality tests, and process capability indices, and so forth. So it's actually a fairly simple process, but it's the computer doing the hard work. Okay? So that's the nice part of it. It's once you have your model set up, you run it, let the computer do the hard stuff, whether it's simulation or optimization, and again, quantify your risk, or in the case of optimization, minimize your risk. A brief note on selecting a distribution. If you have theoretical basis, you would, for example, in reliability work, commonly used distribution is Weibull, and another common distribution is normal distribution. That's something that should be validated with data using a normality test. Another choice is if you, for example, if you have non-normal, you can use the Pearson family distribution where you plug in the mean, the standard deviation, skewness, and kurtosis. Also, if you can do distribution fitting, and we're actually going to show distribution fitting in one of the examples. Now, one of the things that happens often is that you actually don't know what the mean or the standard deviation are, and therefore maybe you have a rough idea of the minimum value, the maximum value, and most likely values. And the three common distributions that are used when you do not have data or solid theory, uniform distribution, for example, is often used to model component tolerances, and it's essentially kind of a worst case, minimum, maximum, and then equal probability of anything in between. Triangular, when you have kind of a best case, worst case, most likely scenario. And PERT is very similar, but it adds sort of a bell shape. It's actually a beta distribution, but instead of a triangular. So some people, like for project management, like to use the PERT distribution. So these three are pretty common in those cases where a priori you don't have, let's say you don't have a lot of historical data, but you do have some process knowledge, and you can apply that to using one of these distributions. Another thing you can do is you can specify correlations. So if you have inputs that are correlated, this picture just shows you this is a bivariate normal distribution with no correlation, and this is with correlation, and just showing you the response surface, what the probability surface looks like, and you can see that they're really quite different. So the bottom line is that if your inputs are correlated, it's really important that you include that in the model, because if you assume independence, then your results are going to be quite different from what they are in real life. In one of the case studies, we will include correlation on the inputs. Now, optimization, I'm going to be very brief here. I just want to talk about stochastic optimization, and essentially what you're trying to do is you're trying to reduce the transmitted variation. So is there an X value that actually reduces the output standard deviation? This is also known as robust design in Design for Six Sigma. And this is illustrated here in the catapult example. We're not going to do that today. That was in a previous webinar, and it's also in the DiscoverSim workbook. Here's a relationship between the response and the launch angle. And if you launch down here, and let's say this is the variation in your launch angle, this is the variation that you see in the response. However, if you shift the angle by 15 degrees, what you do is now you hit the sweet spot. and this is the flat region, and so what happens is then the transmitted variation, this transmitted variation is dramatically reduced. And that's essentially what you're trying to do here with robust design is, is there an X value that minimizes the transmitted variation? Okay, so that's one of the goals. Now, you can have other goals which are simply to maximize the mean or minimize the mean. And there's also complex relationships where there are local minima and global minimum or maxima. And this is an example. It's called a Schwefel function, and a pretty complex relationship where you see lots of different local minima, but there's only one global minimum. And that's why you need global optimization. You can't just use Newton-Raphson type approach, because what will happen is it'll settle in on one of these locals and won't find a global. As I mentioned earlier, genetic algorithms are really good for solving these types of problems. Now, keep in mind here, this is only 2 variables. You can have, for example, you can have 50 variables and this type of complexity going on, and you're trying to find a global minimum in this complex space of 50 variables. Now, it'll take a long time. We've tested DiscoverSim with this exact function in 50 variable space, and it solves it, but it takes several hours to do that. Just to kind of give you a picture of the kind of power that you have available to you. And one of the things we also do for fine-tuning is use sequential quadratic programming. The other thing we do is combine the methodologies, and it's a hybrid methodology, so it takes longer, but it starts with this direct dividing rectangles, then it does genetic algorithm, and then it does sequential quadratic programming. And it also allows for constraints. So if you have, for example, we're going to look at project selection with a constraint, and so you can do the optimization even if you have a constraint. There are a variety of optimization metrics. You can minimize the weighted sum of all of these. You can minimize a deviation from target. You can maximize any of these statistics, process capability indices in here, or you can maximize desirability. Some of you, if you're familiar with multiple response optimization in design of experiments, you probably have used the desirability function. And so we have, so there's lots of different choices here. In the case studies that we're going to look at, we're going to, typically we'll do like maximizing the mean, but sometimes we want to maximize maybe the process capability because we want to not just maximize the mean, but we also want to minimize the variation. I'm now going to turn to the case studies. I'm going to open up the DiscoverSim workbook to show you the case study, and then we'll go in and run it. This is a basic profit simulation. The objective is to maximize profit. It's a very simple model. The revenue is quantity sold times price. Total cost is quantity sold times variable cost plus fixed cost, and the profit is total revenue minus total cost. So what we're interested in is what is the predicted probability of daily profit, and what are the key X variables that influence profit, and can we reduce the variation in profit by reducing the variation in those important X factors. Go to the profit simulation, and this is our first case study. It's a very simple one. 3 inputs, and then the profit is the output of interest. We also have historical data, and what we're going to do is we're going to show distribution fitting on that historical data to come up with the distributions for the inputs. Set up our input distributions here. We set up our outputs here. We have copy-paste. We're not going to use that in this case study. Just a comment, copy and paste. This is DiscoverSim's copy and paste. You cannot use Excel's copy and paste. You have to use DiscoverSim's. And the reason for that is because we have background tables that are created for the input distributions and controls and so forth. And if you were to use Excel's copy and paste, then all those background tables don't get updated. Please keep that in mind. You cannot use Excel's copy and paste. You have to use the DiscoverSim copy and paste. Here you run your simulation. Here's your distribution fitting, specify correlations, and these are used in optimization. And then when we get to optimization, I'll talk about different settings. What I'm going to do here, I want to model quantities sold. And so the first thing I'm going to do is I'm going to model my historical data. So I'll click on Sheet 2, which has my historical data, and I'm going to do the distribution fitting for each of these. So again, I don't have to do this, but because I have historical data, I'm going to take advantage of the historical data, and I'll do the distribution fitting. I mentioned earlier, if you don't have data, then you can use simpler distributions like triangular, uniform, or the PERT distribution. But here we happen to have the data, so we're going to go ahead and take advantage of that. And what I have to do, I'm going to take quantities sold. These are integer values. We're going to try to find a discrete distribution because it is physical quantities. Each unit is sold or not sold. Or if I'm unable to find a discrete distribution, one of the things you can do is you can model using a continuous distribution and then just use Excel's round function. Okay, so that's a little trick that you can use if you want to, if you actually try discrete and you're not able to find a good discrete distribution, then just go continuous and round the output. It's going to give a report of all the discrete distributions, and that was actually pretty quick. And it turns out that the negative binomial is the best fit. That has the smallest chi-square value, and the p-value is good, so we have the negative binomial. You'll be able to pull down from any of these distributions, so you'll have a little drop down, and you're not limited to the best case. You can just pick from the distributions. So I'm going to go back here, and I'm going to model price. This time I will use a continuous distribution. So distribution fitting, and we'll run that. This is now price, and we'll run that. So my, in this case, the 4-parameter beta is my best fit. That has the smallest Anderson-Darling statistic value, and the p-value is greater than 0.05. And as I mentioned, if for some reason you want to choose a different distribution, you will have that option later on. And then finally, variable cost, I'm going to do distribution fitting on that. And I'm going to also treat that as a continuous distribution. And Johnson SB, that's the bounded Johnson distribution, is the best fit. Okay, lots and lots of different distributions. Andrew Sleeper's book on Six Sigma distributions is a good reference for if you want to learn more about the different distributions. And so, as I said, in this case, the Johnson, you may be familiar with the Johnson transformation. This is the Johnson distribution. So what we end up with is we have a negative binomial, discrete. We have the beta, 4-parameter beta, which includes the minimum and the maximum. And then we have the Johnson, bounded Johnson, as the 3 distributions that we're going to use based on the historical data. So now I'm ready to go ahead and create my input distribution. Okay. Now, what I'm going to do is I'm going to go with the stored distribution fit. And this is my quantity sold. And as you can see, the negative binomial is the first one on the list. And so that's actually what I'm going to use. All right, so I'll go ahead and click OK. And then if I hover my cursor, I can see that it's picked that negative binomial distribution. Okay, I'll do the same with price and click Input Distributions. And then I'll come down here to Select Stored Distribution Fit. This is price. And again, I can pick from anything on the list. I'm going to go with a beta. Click OK. And I have a beta distribution. And then finally, oh, by the way, another thing I should have mentioned, when you do have historical data, It is good to look at that data with histograms and with other graphical tools, and SigmaXL is a good complementary tool to do just that, your basic statistical analysis before you just go in and brute force do the distribution fitting. But for the sake of time, we're just limiting ourselves to DiscoverSim here. So now I'm going to create the input for variable cost and put input distributions and select store distribution fit. Pick my variable cost. It's, again, Johnson is a 4-parameter distribution, and then I'll click OK, and there's my Johnson distribution specified. I have, these are intermediate calculations. I have a fixed cost, variable cost, fixed cost, and the output is going to be profit. And again, we use different language. Some of you may be familiar with other tools. They call it a forecast. We're using the Six Sigma language, inputs and outputs. So assumptions and forecasts are in DiscoverSim are inputs and outputs. There is one more thing I want to do before I specify the output, and that is correlations. It turns out that quantity sold and price are correlated to each other. I could use a tool like SigmaXL to calculate the correlation coefficient, but to save time, it's minus 0.8, so that as the quantity increases, the price decreases, which is what you would expect. Under correlations, I'm going to specify the correlation here as minus 0.8. Okay, so this is the correlation between C11 and C12. Now, I could have typed in names. I could have, called this quantity sold and price, and actually in the case study I do that, but I'm just trying to get through this more quickly, so I haven't been filling everything in. So basically, I have now the correlation between quantity sold and price specified as minus 0.8. And then the last thing that we want to do in setting up the model, notice the formula in Excel is total revenue minus total cost. So we go to output responses, and I'm going to put in a lower spec limit of 0. In other words, any profit less than 0, a loss, is considered a defect. This, by the way, target is only used in multiple response optimization, so I can just leave that as is. If you have more than one output, then you would want to specify whether you're trying to maximize, minimize, or hit a target. So, I can change that to maximize, but it won't really affect anything. Okay, so we're good to go now. We have the output specified. Now, what I'm going to do is I'm going to run the simulation, and I'm going to turn on the options here. And what I'll do is I'll add a scatter plot, and I'll add sensitivity charts. Okay, we have other more powerful sensitivity tools, but for the purposes of this demonstration, we're just going to limit it to correlation coefficients. Now, one of the things that's a common point of confusion is the correlations up here are the correlations where you specify the correlations between the inputs. If you don't specify anything, then the model will assume independence. Now, when I talk about the correlations here, the sensitivity charts is y versus each of the x's. And the scatter plot, the correlation matrix, is y versus y if I have more than one output, x versus x, as well as y versus x. So it's essentially a scatter plot of everything. We're ready to run this. Again, I'm using accelerated mode, which means that the calculations are going to be done outside of Excel. We're going to use 10,000 replications. We'll generate histograms, probability plot, descriptive statistics, and process capability report, as well as the correlation matrix and the sensitivity analysis. This is our output report. We have a mean profit of $389, a standard D, pretty large, $179. If we're looking at process capability, 0.7, not so good. 1.5% likelihood of a loss. What can we do? We can go to the sensitivity chart. So variable cost is the most important X factor that influences the variability in profit. So variable cost followed by quantity sold, that's what I'm most sensitive to. What can I do about that? All right, if I want to improve my profitability, I now know which X factor to go after. In this case, variable cost. And then we also have the scatter plot matrix, so you can get a nice visual of the relationship, the different relationships, and the correlation matrix. This is all the inputs and outputs versus each other. So you get all the information consolidated. Okay, so that's the first example, and that was just straight simulation. The next example that we're going to use is now going to look at optimization, and that's a magazine production example. It's actually a simple example, but a nice way of introducing optimization. We have a magazine publisher wants to determine the optimal magazine production quantity to maximize profit. Monthly demand, in this case, we have historical data, but we're not going to use distribution fitting. What we're going to do is we're going to actually specify a custom discrete distribution. We're going to use what's called an input control. Now, in other tools, a control is also known as a decision variable. Actual production costs, we have disposal costs somebody has to go and pick up. We have to pay to have those magazines picked up. So it's the disposal cost is a smaller cost than the production cost. So the revenue is going to be the lesser of monthly demand and monthly production times the selling price, and the production cost is the magazines produced times the production cost. Total disposal cost is only in the situation where we have more magazines produced than we have demand, then that number will be multiplied by the disposal cost. Finally, profit is revenue minus those two costs. So it's a fairly simple model. We'll now look at our model. For convenience, I have the custom distribution set up where with each quantity I have a weight associated. This probability number is calculated. It's simply this weight number divided by the total of the weights. Rather than having you put in a probability number, what we do is we have you put in a weight. Putting in a weight is a little more intuitive than an actual probability. So in other words, I can say, well, I think we have a better chance of selling 20,000 magazines and an even better chance of selling 30,000. So in this custom distribution, you simply put on the weights. And this is based on past experience, kind of like a triangular distribution, but you're just putting in more information. So we're going to say that the most likely outcome is 50,000 magazines per month. But it of course, then drops off as the numbers get bigger. So that's our data for our discrete distribution. And what we're going to do now is I'm going to create the custom distribution for demand. And I'll go to discrete, custom. And what I have to do here is I have to put in the data range. So this is my data range. And then I also have to put in the range for weights. All right, and I'll update the chart. And this is my custom distribution. By the way, the chart shows you the probabilities, so it converts the weights to probabilities. All right, so I'm going to, just to make it a little easier to interpret things, we'll put a name in here, and we're going to call this demand. And then click OK. All right, so there's our demand distribution. Magazines produced. This is going to be an input control. And what we're going to do is then whatever number we put in will be multiplied by 10,000. Currently, our input controls are limited to integer values, so I can put a lower value. For example, I can say 1 to 10, and it will increase from 1 through 10, and then I'll just multiply that by 10,000. All right, so to do that, I come over here to my input control. I'll give this a name. I'll just say production. And again, it's discrete. I'm going to start with 10. By the way, we'll say 10 is our current value. That's 100,000 a month. Minimum of 1, which would be 10,000, and a maximum of 10, which would be 100,000. Okay, so that's my input control, also known as a decision variable. Now I put in my output. My output is profit. I have, again, intermediate calculations of revenue, the production cost, and the disposal cost. So I put in my output response. Well, again, as we did before, we'll say our lower spec limit is 0. So in other words, anything less than 0 is a loss, is a defect. I don't really need to change this, but I'll just change it to maximize. It's only used in a multiple response optimization situation. So with that, and I'll label this as profit. Click OK, and that's my my output. I'm now ready to run the simulation. And we'll run it. Of course, it is a discrete distribution. We have an expected mean of 42,300 per month. But notice how big the standard deviation is. Okay, so lots of variability here. So we're gonna make money here, but then these are the months that we lose money. And turns out that if I look at the actual performance, there's a 23% chance that we're going to lose money. So question is, well, can we do better than that? In a case like this, the problem is so simple, I could just type in different numbers. I could do 10, 9, 8, 7, 6, run the simulation, see what I get, pick the winner. But keep in mind, this is a simplified model, and it's just to illustrate the concept. And we're going to run the optimizer, and it's going to pick the best solution. But if you have multiple variables, or if you have continuous variables, then the problem becomes much more difficult, and it's not the sort of thing that you want to do trial and error on. What we're going to do now is we're going to maximize the profit. So to do that, I'll hit Run Optimization. I'll change this to Maximize. I'm going to use the mean. I have 3 choices. I can use Hybrid, or I can specify. In this case, just to speed things up, I'm going to go with the genetic algorithm because it's a simpler problem. If it's a more complex problem, I would use hybrid methodology. All right, so we'll go ahead and run that. As you can see, so what the recommended value, it's predicting a mean profit of 61,000. So we've definitely seen an increase, and that's 60,000 magazines a month. I click Yes. And here, as you can see, it's populated this control value with 6 now. So that's the expected optimum. So now I'll run my simulation at that value, and we'll see what we get. All right, so there's the new distribution. There's our mean value based on the simulation, 59,000. You compare that to the earlier predicted 42,000, so we have a nice increase in the mean. We have a reduction in the standard deviation, and we have a reduction in the expected percentage of probability of a loss. So it went from 22% likelihood of loss to 5%. Okay, so that's your magazine optimization. That's a very simple optimization problem, but it illustrates the power of the tool. The last example that we're going to use is a more complex one, and that's picking projects. So what I have, and acknowledgments to Dr. Shaw, Harry Shaw, contributed this example. We have different Six Sigma projects, and each project has a certain likelihood of cost savings, a minimum, most likely, and a maximum. So we're going to use a triangular distribution. And what we have a situation where we want to maximize the total expected savings, but we have a resource constraint, no more than 20 people, 20 people max. Furthermore, management requires a minimum total project savings of $1 million. So that's the limit, or that's the lower spec limit. So what we have is our minimum savings of $1 million, a limit to the number of resources of 20. We also include the probability of success, and we'll specify the resources required. So let's have a look at that model. I have here 9 projects. We're going to use a triangular distribution where we have minimum, most likely, and maximum in terms of savings, expected savings. Furthermore, we have with each project a certain probability of success, obviously based on the complexity of the project. As you can see, Project E, the savings numbers are quite big, 1.5 million to as high as 2.5 million. However, there's only a 50% chance of success, and it requires 10 people. But what we can do here, we can run Optimizer to see, given our resource constraint, what are the best projects to pick for us to work on. Now, keep in mind, if I decide not to do a project, that doesn't mean you can't do it later. But in terms of setting your priorities and helping you to manage your risk, this is a good example. I'm going to put in a triangular distribution for each of these projects. So I'll click Input Distributions. I will specify triangular. The minimum is here. The mode, or most likely, is here. And the maximum is here. The line changes to an arrow just to indicate that this is now a referenced cell. The project name, I'll put that in. I'll update the chart. This is my triangular distribution. I have everything ready to go, so I'll click OK. And I can click on here to view the graphical, look at the distribution graphically. So I'm now going to copy and paste. Again, please do not use Excel's copy and paste. You have to use DiscoverSim's copy and paste. So I copied. I'm going to paste. And what's going to happen is it's going to pick up on the project name and the min, max, most likely, for each of the projects. Now I'm going to do the same thing with the probability of success. This time I need to use a discrete distribution. We'll go to discrete. And the distribution is Bernoulli. It's basically yes, no, pass, fail, 0, 1. Okay, flipping a coin. Flipping a coin would be an example with an event probability of 0.5 because equal chance. Here, the probability of success is specified by the value here, probability of success. I can update the chart, and there's my 0.9. Also, I'm going to put in the name for probability here. So I've put in the event probability, and we click OK, and we can look at that. Now, I'm also going to copy and paste, so I'll copy that, again, using DiscoverSim's copy and paste. We'll paste those. That takes care of the probability of success. Probability of success then is multiplied by any cost savings. In the simulation, obviously a lower probability of success will mean a lower expected value. Finally, resources. That's going to be an input control, a 0 or a 1. Either you pick the project or you don't pick the project. Here we'll go to input control. The name, I'm going to specify the name here of my input control. It's discrete. I'll start with a 0 value, and it's basically just 0 or 1. Click OK. again, I'm going to copy and paste. So I'll copy that, and then we'll paste. So now our input controls are set up. Again, it's integer, 0, 1. The optimizer will then select the projects. Basically, 0 or 1 will determine the selection. The last thing I have to do is I must put in the constraint. So I'm going to use this field here to put in my constraint, total resources. Conveniently, I have this cell, which is a sum product, which is this number times the resources required, and it's all summed up. Okay, so I'm basically saying this value has to be less than or equal to 20. So I go over here to constraints. So I just have the one constraint. I'm going to put in on the left-hand side is 024 less than or equal to 20. So that's my constraint. Whatever projects I pick, I have to satisfy that constraint. Last thing I need to do is I need to specify the output, which is, of course, the expected project savings. If the project is selected, then it's going to be equal to this savings value multiplied by the probability of success. And then this is the summation of those numbers. That's my expected total savings. So we'll put in our output response. I'm going to call this savings, or total savings. The units here are in thousands. Everything is in thousands. So I'll put 1,000, which corresponds to $1 million. So I want to maximize my savings, although, as I mentioned earlier, you actually technically don't need to change that. That is our output defined. You can, again, hover to just confirm that everything is correct. Now we're ready to run the optimizer. By the way, I'm not going to run simulation right now, because if I do, I'm not going to get anything because I haven't picked any projects. So it wouldn't make sense to run simulation without any projects selected, because basically you'll have 0 expected cost savings. I'll start off with maximizing the mean. Because of the time constraints here, I'm just going to go straight to genetic algorithms so you can see how it works, and let it run. And what I will do is I'll actually interrupt it, and then I'm just going to manually type in the values that it's going to pick. Because the problem is this optimization takes about 5 minutes. But we'll manually type in the values and then run the simulator. Under the first run, the projects that are selected are Project C, Project E, and Project H. Okay, and that's kind of intuitive. These are the ones that, these are the high dollar projects. And then we'll run the simulation. And the expected savings is $2 million, the mean value. But look, we're all over the map. And, there's also a 22% chance of savings less than $1 million. But instead of maximizing the mean, what we can do is we can maximize the process capability. So since there's only one specification limit in the workbook, we use PPL, which is the process capability, process performance lower. So again, I won't run it. What I will do is I'll just run the simulation with the values that are chosen. So it's really a different set of projects. Selects Project A, Project C, and the important one is that it does not select Project E. All right, and then comes down here, and these are the projects that are selected. And of course, the constraint is satisfied. So I'm going to now run the simulation, and our mean savings are a little bit less, 1,900 or 1.9 million. However, notice that if I compare standard deviations, the standard dev has been cut in half, and the likelihood of failure to meet management requirement has gone from 22% actual 4.5%. So this is really a better solution in terms of projects selected. Compare the two scenarios. The big issue here is this one project, Project E. So you can then say, well, maybe we could break it down into smaller projects. So maybe is there a way we can increase the probability of success? Is there a way we can do with fewer resources? These are things that you can look at. It turns out if you run a sensitivity analysis, of course, if I run everything with a sensitivity analysis, project E is the most important contributor to the variability in cost savings. You can concentrate on that one, and in this case, the recommendation would be to hold off on project E, do the other projects, get your savings, and then you might want to consider taking on project D downstream. That concludes my presentation. Thank you very much.